I'm Mr. Black, and tonight we're going to start kinematics. Kinematics is the study of motion, and we're going to begin first with describing motion. This correlates to 2.1 in your textbooks. You're going to hear this video is narrated mostly by Mrs. Avon, who still teaches here at Mars High School. She's just working with technology consultants, so Mr. Kropauer is taking her position. But to get us all on the same page, we kind of began kinematics when we were on Route 228 looking at speeding cars. And in that situation, we can simplify the entire universe, the entire world, into like a single line, almost like a number line. And this is how we're going to begin physics. We're going to start on one dimension. Now, on that one dimension, we need a place that we call zero. We're going to learn later this is kind of a lie in physics. There is no such thing as a zero motion. But for a study, you can set this zero motion. For us, it was the beginning of the tape measure. And we'll learn in the reading today and in this movie that that's something we call the origin of your motion. It's kind of an artificial zero mark. You also may recall you set a endpoint. And upon doing that, we're going to find in kinematics that you've pretty much established a direction. That car, when it passed the zero and you started the stopwatch and went to 25 meters, it was moving in a positive direction. And you also could measure the time elapsed. You got that from your stopwatch. For instance, you may find that the car moved that 25 meters in 2.00 seconds. And so we already see some introduction to kinematics. We could talk about the car moving in a positive direction, but had it instead been in the opposite lane, moving this direction, you would have seen on the meter marks would have been going down from 25 to 24 to 22, passing the origin. So you're going to learn in this chapter we can even talk about negative direction motion. So we can have both positive and negative direction along a line. And of course the zero, what we use to establish this beginning, this set beginning we agree upon, is our origin. So you'll hear a lot more about in the video we're going to see today. Miss Avon begins her video pretending that we were in place. We had our tape measure stretched out up to 30 meters, and suddenly a runner came by, and we had a camera so we could take a picture of that runner once every second. He might start at the origin, 1 second later he's at 5 meters. We wait 1 more second, take a picture, and then every preceding second we can take a picture, and that's a way we can actually picture the motion. So it's another way of doing kinematics. That'd be called a motion diagram, and that's where she begins.
If we were to measure this runner's distance and time, what we have done is we have defined a coordinate system. A coordinate system is just a location of zero for the dependent variable. I don't know if the runner was running before I set my coordinate system at 0 meters. It is possible that he was running prior to that, but by defining my zero for the dependent variable, I'm establishing a coordinate system. I'm also establishing what we call an origin, and I'm sure you know an origin from math and from any graphing that you've done in other classes. That's where both variables, in our case, would be distance and time, are 0. So we can compare the runner's location to the origin using an arrow, which indicates position. Position is just a separation between the object and the origin, and the length of the arrow represents the distance from the origin. So in letter B, you see 2 different arrows. You see one arrow at the top, if you can see it, it's green. That shows an arrow from the origin to the position at 2 seconds, if we're going to call these 1 second intervals, or at 10 seconds, if we're going to call them 5 second intervals. Typically, if you need to get numerical data, the book will tell you what the time interval is between each point. Then we have a second green arrow that represents position at a different time interval. So this is arrow number 2. That would be at 1, 2, 3, 4, 5, 6 seconds if we assume 1 second intervals. Okay. So we have arrows that we can describe with a tip and a tail, and that will come in handy when we talk about vectors later in this section. So the arrow is just representing the distance from the origin. So not only can we look at what we know about this object based on the picture, if we add some numbers, some quantitative data, we can also start talking about specifics. Where is an object at a certain time? And we can begin answering those questions that we set out to do at the beginning of the section. Where and when. In these pictures, we see positive positions. We have to ask ourselves, is it possible at this point to have a negative position? And the answer for us is a very emphatic yes. When we look in physics at different pictures, it is very important for us to understand that a negative position is actually a very important aspect of physics. Negatives and positives are going to be essential to our understanding of the motion of an object. So in physics, the sign of our numbers is extremely important because it indicates direction. And direction changes the fundamentals of how we add, subtract, and work with these numbers. In math, in our mathematics class, numbers are typically scalar, S-C-A-L-A-R, and a scalar number refers to magnitude only. So when we add scalar numbers, we get a sum. So in math, 2 plus 3 equals 5. However, in physics, 2 plus 3 does not necessarily equal 5 if those numbers are vectors. What that means to be a vector is that a number not only has magnitude, but it also has direction. So we said scalar numbers from math. We will be working with scalar numbers in physics. A distance, a speed, time, and mass. Those are all scalar numbers. They don't have to have direction associated with them. However, vectors, we're going to look at position and displacement today, and then velocity in our next lesson. They have both magnitude and direction, and they are in fact represented by arrows, which is what we saw on the last slide. We draw the tip of an arrow to indicate the direction that that arrow is in. So if we look at the picture from your house to the store to your aunt's house, we go 5 meters to the store, and we can call that east, we can call that to the right, we can call that positive. There are several ways to show direction in physics. Then from the store we go another 2 meters east, to the right, forward, or positive, whatever we choose to be our indicator of direction. Okay. So when we add vectors, we don't just call it the sum because it's different than adding 2 plus 3 and getting 5 in math class. We call it the resultant. And the resultant is just the sum of 2 or more vectors. We have looked at distance and we have looked at position when we were talking about the earlier slide. Distance is how far an object moves. Position is the location of an object at any instant. And we said that the position has to be from the origin. So if we were to sketch out an object that's moving, let's say it moves north, then east, then south, then east, then north, then east, then south, then west. Okay. If I assigned numbers to these, let's say it moves 3 kilometers, 3 kilometers, 3 kilometers, 2 kilometers, 2 kilometers, 2 kilometers, 1 kilometer, 2 kilometers. In order to get distance, just like I would in math class, I simply add them up. 3 plus 3 plus 3 is 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. The distance that this object moves is 18 kilometers, just double checking my math there. So it moves 18 kilometers. For distance, the path that an object takes matters in your calculations. It is essential that you take into account every step, in other words, or every bit of movement that the object covers. Position and displacement, however, are very different because they only take into account the change in position. The difference between position and displacement is that position is always from the origin. Displacement is between any 2 points. So if I wanted to look at the position of this object, I have to start at the origin and go to the end. So I would need some way to measure not only the length of that vector, but also its direction, which, as you can see from 0, is at an angle. So we can't just imagine or sort of make up a number for the displacement in terms of direction. We're actually going to have to measure the angle, and we will learn how to do that in future chapters. If I wanted the displacement between this point and this point, then I would have to figure out a way to find not only the length of that vector, but also its direction. So in physics, we can't say that 2 plus 3 is necessarily equal to 5. It would depend on the direction of the original vectors. When we again look at these quantities, we really have to understand the difference between a scalar quantity, which we can just simply add, and a vector quantity, which we have to look at also the direction. So we can say that displacement is going to be a distance, but it has to be plus a direction. And that direction is very, very important when we start studying the motion of objects. Okay. When we look at vectors again, and we try to add them, we said we can't add them just like we do in math class. The same is true when we want to subtract vectors. And this is the very last piece of the first part of the chapter. When we looked at the picture before where we went from our house to the store to our aunt's house, what we did was we took 5 meters and 2 meters, and the resultant was 7 meters. So we just added those two because they were in the same direction. And then this, which we call the resultant, always goes from the tail of the first vector to the tip of the last. Okay, that's another way to define the resultant, not just that it is the sum of 2 or more vectors, but that it goes from the tail of the first vector to the tip of the last vector. So if I want to add 2 vectors, one that is 5 meters to the right and one that is 2 meters to the left, my resultant going from the tail of the first to the tip of the last would be 3 meters. Okay? So typically you would see the 5 with a positive, the 2 with a negative, the 3 with a positive. Okay? Typically we say to the right is positive, to the left is negative, because that's the Cartesian coordinate system that we've learned to graph on from way back in math class. Also, addition is different when you have vectors, but so is subtraction. So if I have vector A plus B, let's say A again is 5 meters, and B to the right, or positive 5 meters, and then B is going to be positive 3 meters. Okay? Because they're in the same direction, I can just add them to get 8 meters. If, however, I want to subtract A minus B, in physics we don't really subtract vectors, so we're going to rewrite this expression as an addition sentence. So A minus B is the same as A plus negative B. So when we go to subtract vectors, I'm going to take A, which was a positive 5 meters, and I am going to add it to a negative B. Very important in physics that positive and negative only indicate direction. Okay? There are no such thing as negative numbers when we're talking about vectors. They're just telling us the direction that the object is moving, or the direction of the velocity, or the direction of the acceleration when we get into later chapters, actually later in this chapter. So if I want to take a vector and make it negative b, I simply have to reverse its direction. So instead of being 3 meters positive, a negative b would be negative 3 meters. And then I just go about adding them like we had in the previous examples. So I have 5 meters, 3 meters. My resultant, I guess making it a different color would make it easier for you to see, is from the tail of the first to the tip of the last. It would be a positive 2 meters. So we're going to spend a good deal of time in class practicing working with vectors, because they're not like mathematical numbers. We have to make sure that we include in our scenarios the direction.